What's up, everyone? Hope everyone is doing well. Um, Hopefully this is just a short video, but I am currently in the process of wrapping up this month doing preventative maintenance on equipment that's scheduled for the month of January, and that includes this Eppendorf centrifuge. And I powered it off to inspect it. So what I'll do is I will check these, for example, these vibrational mounts. I'll make sure the brake resistors are measuring the correct resistance. Just do a general cleaning, inspect the main circuit board, and also what the lid assembly. Make sure that it's greased, it's moving freely. Just some minor stuff, cleaning the chamber, cleaning the rotor, and then of course making sure it's spinning at the appropriate that the speed is accurate. So anyway, got ready to power it back on. This thing was working completely fine to my knowledge. It was on when I first got to it, and now it will not power back on. So now I wouldn't be surprised if there's already a video out on repairing one of these, because they're pretty notorious for this. There are two capacitors in the buck converter circuit. You can see those two right there, right by that 7805 5-volt regulator, that tend to go bad. Mainly this little guy, which is a lower capacitance. And what'll happen is most people will leave these things on 24/7 like we do here, and then finally you go to shut it off and it won't power back on. And generally it's due to that capacitor. So let's take a few measurements. I did verify that this what is it, the UC2844 AD, so that's the current mode PWM. I did verify that it is getting the voltage, but that's as far as I got. It's likely going to be those two capacitors, if we're lucky. Anyway, let's give it a go. Alright, so I thought it'd be cool to kind of go over this main board a bit, the topology, how it works, before we dive right into it. And I've already done a video not all that long ago on Eppendorf centrifuges. That was for the 5804, 5810. And I had mentioned this model, which is the 5415D, and how they do kind of suffer from some of the similar problems. I've seen a number of times where these boards will end up with a short on the 5-volt rail that takes out all of the digital circuitry, and I just don't see that happen in other manufacturers like Thermo, Sorval, Beckman. I never see those types of failures, but I've now seen it across multiple models of Eppendorf centrifuges. But that being said, let's just zoom in here a bit. Not the best lighting, I apologize, but well, we'll start here with the mains input. It goes through some filtering. This is all EMI filtering. This here is your bridge rectifier. So you've got some additional filtering. This is your main filter cap, this large cap right here. From there, we'll need to zoom in a little bit. They've got some sort of offline flyback converter going on here. Alright, so if you look here, you can see some resistors that kind of go in a line, and there's a couple more back there. These are taking that high voltage coming from this capacitor at 160 volts. It's regulated DC, coming from that, and it's being stepped down, and then you actually have this not Zener, but this diode here, and then it ends up going on to this UC2844 C824 which is your current mode PWM. That's how this thing gets the supply voltage, through this series of resistors that are stepping the voltage down. All right. And you can also see here, there's some current sensing going on here. So this is your current sense resistor here. And, you've got a network of resistors that finally makes its way back to the current sense pin on the PWM controller. All right. This is your switching MOSFET. Okay. And so from there, the drain to this connects to a winding in this flyback transformer. What's interesting about a flyback transformer is it's more of like a transfer of energy. So your secondary and primary windings aren't going to be you're not energized at the same time like you would see in a normal transformer. So that's, you've got a winding here, and then you've got two other windings. You've got two secondary sides, and one is delivering voltage to this 5-volt regulator here. And this is the capacitor for that secondary side voltage, this filter cap, and you've got some rectifier diodes as well, a rectifier diode. And then if you look here on this side, you've got the filter cap for the other winding rectifying diode, and then they also move on to another 5-volt regulator right here. So this 5-volt regulator is what is supplying voltage to your digital stuff here. Like this is your microcontroller, your EEPROM, E2PROM, and then all the glue logic that's going on. This microcontroller is doing all of the motor control. So it's not like that other 5804 where they've got separate microcontrollers driving the motor specifically. That's all being done on one microcontroller right here. You've also got, they do have some isolation going on here, it seems like, and some optocouplers here, and it does seem that is isolated from the motor driving circuit. The motor driving circuit that has the inverter, which is interestingly on the bottom of this board. It's on a separate board actually, which I can show you guys right here. This is it. So that's underneath it. We'll see that in a second when I try to replace, I think it's going to be these capacitors. Again, that's best case scenario. The fastest, hopefully that's what it is. But anyway, this guy is sitting underneath this board, and you can see here you've got your 6 transistors to provide 3-phase power to the motor, the BLDC that's right above the unit. And then interestingly, they've also got, you can just barely see it, this IC right here. This is a power factor correction IC, which is bringing the power factor as close to 1 as possible. That the power factor is going to change based on how much reactance you have in your circuit. So you have a lot of capacitors or inductive loads, for example, like this motor, that's going to bring the power factor down. And when you have enough of devices like that connected to the grid, that can cause issues. And so, this is I don't know if this IC is always in play. It may be only when the motor is driven, but I'm not 100% sure. But anyway, if you look here, what the power factor correction IC is doing is it's boosting the that voltage. Usually it's upwards of it's usually upwards of 400 volts for power supplies that are over the range of 85 to 265 VAC, it will cover that entire range when the voltage is boosted to that level, and that will require a boost MOSFET, which I believe is this guy right here. And then of course you've got this this would then, I would assume, be your resident you know, part of the resident or tank circuit for that boost converter, this guy right here. And then you've got your brake resistors connecting here, so this is your brake circuit right here with maybe a MOSFET switching that brake off and on. Some comparators going on right here, doing some sort of sensing, but that's basically it. And so we're going to we're going to diagnose this power supply. Again, I've already checked the supply voltage to the current mode PWM, this guy right here, and it is there. What's interesting is that this little capacitor is what's filtering the supply voltage to this IC, but this is usually the one that goes bad. So maybe it has a lot of ripple on it that's causing some issues with the chip not starting up properly, but we should be able to determine that. So let's get started. Okay, so as I said, I've already checked the supply voltage to this IC out in the lab, but we'll just do it one more time on camera so you guys can see. And I'm just going to be probing I've got my meter leads crisscrossed. Alright, let's try that again. And you can see, but look at that, look how that's fluctuating around like that. That should not be happening. And so, why don't we probe this guy with the scope and see what's going on there, because that just doesn't seem right. But 15 volts for this particular, for the UC2844, is well above the threshold voltage for it to turn on. Well, we got the scope. You guys can see the scope, and let's probe that VCC pin. Oh. Yep, something weird's going on. Uh-oh. Well, it was doing something strange, and now it's not. So we are at 14 volts now. Yeah, I don't know what that was about. This is AC coupled, it's not. It's a bit weird, a lot of noise. Yeah. But that looks much more normal. It was doing something really strange earlier, if you guys saw that. I don't know what that was about, but... And that's the output to the PWM. So that all looks good. And if you look down in the bottom right corner, we have 5 volts on our 5 volt rail. So yeah, I don't know. I think we should just replace those caps anyway, but yeah, it appears to be working now. And we have 5 volts on our other regulator too. So power supply is working. It's working fine now. Well, that was really strange, but again, I'm still going to replace that cap. Maybe both of these, all 3 of these electrolytics. to get this board out, you've got to remove a screw right here. Don't remove these screws yet. You're going to need to disconnect the motor cable as well. And then the screws, there are 4 screws on the bottom, these 4, that you will remove to get the board off. And then of course you're going to disconnect this connector, and then your mains connectors and the brake resistors, but that should get it free. Alright, so we've got the board removed, and then you want to remove these 4 screws which are on the top. Do that once you have the board out, and then you want to be very, very careful with lifting this guy up. It's a, you know, if you're good with soldering, it's not the end of the world, but sometimes these guys will break, and then, you know, they'll lift up if you're not gentle with just removing this, because unfortunately you have to bring the inverter board up and away from the PCB to access these capacitors. So you have to do that. Just be really careful and try not to break any of those pins. But we're going to measure these now in circuit and see how they look, see what their ESR is. Alright, so I know you probably can just about see this, but let's take a look here. Let's bring the frequency up to 100 kilohertz, because that's technically how these are measured. And that's 2.52, which isn't, it's a 22 microfarad cap. But if we look at it at 1 kilohertz, it's really high. It's at 155 ohms. And yeah, so, and again, we're going to take this out of circuit. It should be 22 microfarad. For comparison, here's that other cap. Yeah, and that's a 220 mic, and you know, we're at 100 and almost 200. That's within spec, you know. So ESR is low. So I think that's the culprit. So I'm gonna remove this guy. I definitely have one of these on hand, but we will take it out of circuit, do a final measurement. Another thing that's interesting is if you look, you've got all this residue. Like, what is that right there? It's not really coming up there. Oh yeah, yep, look at all that. Look at that. This almost looks like dendrites that, you know, that these can form these ion channels on the board due to old flux during the fabrication process, and they can actually form these conductive bridges between points on the circuit board, and that's why you almost kind of see these branches coming out. You tend to get these in high moisture environments, but that almost looks like what we're seeing here a little bit, and that can cause issues. But I think in our case, it is this capacitor that's the problem. Yeah, so that is with the cap out of circuit. And this is technically at, you know, technically you're supposed to report ESR at 100 kilohertz, or that's what the manufacturers reported at, but I mean, this is still way too high. Way too high for a 22 microfarad cap. And it's not even measuring 22 mic either. That's the most important part, I guess, but, yep. So, does appear to be this cap. Maybe when we probed it, it was just enough of a jolt to, you know, change in impedance, or who knows what happened, that was enough to wake the PWM up and get it running. And that's why, you know, it started outputting a PWM signal to the switching MOSFET, and that's why we got our 5-volt rails back up. That's probably what happened. But anyway, I'm gonna pop a new cap in, we'll reassemble this thing, and we should be done with it. Yeah, and so once you flip this guy back down, you do want to check just to make sure that you know, all of your pins are still connected. They haven't broken free, because it is very easy to snap these off. So just be aware of that. Yeah, and so that looks a lot better. Sometimes when you clean these types of this type of residue with just IPA, you'll notice once the IPA dries that it's still there. This looks a lot better, but you can see that, you know, there's still some of it there. You might want to try something a bit more abrasive, or, you know, but it's not the biggest concern. It looks a lot better though. All right, let's see. Moment of truth. Will it turn on? Hey, there it is. Came on nice and quick. All right, that's what we want to see. Cranking it all the way up. Oh, yeah, well, you lose it occasionally. Yeah, there you go. 3.2 RPM. There it is. Brakes nice and quick. No weird noises. Some of these models, and lid works. I haven't really seen this with the 4515, the 5415Ds, but some of the similar sizes, like the I think it's the 5418. The brake resistors on those will go bad very quickly. And they're not nearly as beefy as the ones in the 5415D. So if you're seeing the centrifuge take a very long time to slow down, it's those brake resistors. Unfortunately, on those units, if you don't have a lot of experience with soldering, they're on the main board, whereas you can see clearly those are not. So, you know, you got to be a little delicate with those. But this one is looking good to go. That was pretty much the end of my PM. That was the last thing I had to do, and then the thing stopped, just wouldn't power back on. So I'm going to put a new PM sticker on it, and we will see this thing again in another year. Very interesting what happened there. Clearly it was that capacitor, which one it is escapes me, but I'll embed it in the video. But it's across the supply to that PWM controller, and you could clearly see on the scope it looked like it was doing some sort of hiccuping where it was trying to start up, and you could see the voltage ramping up and down, and then finally it just went stable, right? And it could have been due to, again, us probing around, and gave it just enough of a jolt where it was able to, the controller was able to turn on, and once it was on, it was stable and good to go. But power this thing down again and the same thing probably would have happened. So it's a common issue with these, but 90% of the time, if these aren't powering on, it's that capacitor. I hope you guys found that interesting. Working on a few other videos in the interim. This just sort of popped up, and I figured I'd just knock this out real quick. Thought it'd be pretty cool. Show you guys a little bit of the circuitry. Yeah, if you have any feedback, leave it in the comments, and I'll catch you at the next repair. All right.